So I'm going to move away from testing now and say a bit about measuring association. So we're now back to continuous data. You're going to think about, you've got two continuous measurements and you want to know if they're associated with each other. And you want to be able to measure that association. So if we first of all think about measuring the association, then there's something that's called the correlation coefficient that conventionally gets used. Just to give a feel for what this coefficient, what sort of numbers you might expect from it. If you imagine this is sort of two measurements, one plotted on the y-axis, one plotted on the x-axis. If they fell in a line exactly like this, you could put a straight line through them, you would say they'd got a correlation of 1, and this R is often used to denote the correlation coefficient. If there was absolutely no relationship between them, then correlation would probably then be close to 0. If they were on a line but it was sloping downwards, then correlation then would be -1. But usually you're somewhere in between. You're never exactly 1, 0 or -1. You're somewhere in between. So you'd expect it to look something like this, sort of dotted around a line if it's positively correlated, but not exactly on that line. So depending on how close these dots are to the line, you'll get the level of correlation. And so here we've got a correlation coefficient of 0.6. So this positive correlation, it's saying, yeah, we're measuring an upward slope, but it's not exactly 1 because the values aren't formed on that straight line. And the same for this negative correlation. It's not exactly -1, but it is definitely negative. Correlations can be calculated by hand, but almost certainly better calculated now in a package. And the usual correlation coefficient that you calculate, which can be denoted by R or sometimes ρ, is known as the Pearson correlation coefficient. So that's the conventional correlation coefficient that gets calculated. However, if your data are really sort of badly distributed, because it does assume a fairly symmetrical or normal distribution. If you had an odd distribution, it's useful to know there is another type of correlation available which works with the ranks of the data. Sorry, I'm jumping ahead. I'll just show an example of an ordinary correlation to start with. This is some data from that trial of newborn calves, had various measurements taken, and this is 2 of them. We've got white blood cell count on the y-axis, and we've got platelets on the x-axis, and these are the sort of plots of the values. And you can probably see from that they sort of look as if there's a positive slope, so that is an indication they're associated, and the correlation coefficient, sure enough, is definitely positive. But what I was coming on to say, I jumped ahead a bit, is that if you've got non-normal data or data with an odd distribution, it's good to know that there is another type of correlation coefficient known as the Spearman rank correlation coefficient. So that works with the ranks of the data, the order of the data, and correlates the ranks rather than the original data. And so that's more appropriate if your data are not normally distributed. And if that's calculated for this same data set, that came out to be a bit different, probably due to this outlier down there. That's probably had a big influence on the correlation. So you'd have to think about whether that outlier was a wrong value or there was something odd about it, and whether you could justify taking it out of the data. But if not, you're probably better working with this rank correlation coefficient.